Right after the test, you should have picked up these notes. Starting in the chapter 4. Chapter 4 is something that you should have seen all of this content before at some point, but we will go over it. And probability really is setting the stage here in this chapter for inferential statistics that we'll get into later in the next 9 weeks. So for this page, what I would suggest that you do is maybe pause the video and fill in the blanks, or you may be doing that already as you listen. This is some terminology associated with probability and probability experiments. And at the bottom, I will give some sample examples and talk a little bit about some of the terms on this page. Make sure you understand and are familiar with all of these terms. Probability is the chance of an event occurring, and like I said, it's the basis for our inferential statistics, which we're going to cover later on. Investment insurance fields really do use probability to do pricing and to make predictions, and we're going to see that in Chapter 5 as well. All right, so fill in the blanks for these terms: a probability experiment, an outcome, a sample space, an event, and then an event being a simple event or a compound event. So fill those in. If you need to, pause the video to get them down, and also fill in these 2 examples in the table at the bottom. I'm going to start to talk about the bottom so that the video can be as short as possible going through these notes. So I gave an example of an experiment. The experiment is tossing 1 coin. In this experiment, the sample space, which is the set of all possible outcomes, our possibilities is that that coin is going to land on heads or tails. An event consists of a set of outcomes of a probability experiment. So maybe the event is something that we're interested in knowing the probability of. So I listed here, which we're going to come to know this as probability notation. What's the probability of the coin landing on tails? This event, because it only consists of the outcome of landing on tails, is called a simple event. Let's compare this to the other experiment where we roll a die. In rolling a die, here is our sample space. The sample space has 6 possible outcomes. And let's say the event that I'm interested in is the event that the die would land on an even number. Here I pointed out the even numbers, which I hope everyone does know that already. And because probability of landing on an even number contains multiple of our outcomes, we call this event a compound event. All right, so the next thing, I'm also going to just turn the page, and I'm going to use a already filled in copy of the second page to talk about a tree diagram. All right, a tree diagram is used to determine all possible outcomes of a probability experiment. It's really a way so that you could determine all the possible outcomes. Whenever it's not as clear and as easily found, a tree diagram can help you organize that. So I have an example here of a tree diagram that represents the sample space for a sequence of a result of 3 coin tosses. So not just tossing the coin once, but then another time and yet another time after that. A tree diagram has a starting point, and that's the point over here to the left-hand side of the page. From here, the branches actually represent, how many outcomes could be possible when we toss that coin. Well, we know the sample space of a coin is just heads or tails. There's 2 possible outcomes. From there, every time that we go further along our branches, like on the second coin toss, we have to start to construct what would be the sample space of all 3 coin tosses. In the end, we follow along the branches to list the sample space for tossing 3 coins. And what we see here is that we have 8 possible outcomes. We could tell that we had 8 possible outcomes just by counting how many branches we have at the very end of our tree diagram. However, Something like this, we could further answer probability questions knowing this sample space. For instance, what you see that I have checked here, what if I said, what's the probability that 2 of the 3 coins land on heads? There are 3 outcomes where 2 of the coins land on heads out of a total of 8. Probability notation is the next thing here. The probability of an event occurring. So we put P and then in parentheses, this E represents whatever the event is. Not only is the notation important for today's lesson, it's important through pretty much the end of chapter 6. Probability notation will help you keep a lot organized and understand what your event is. Another thing that is very important, I have them starred, you're going to see this on your multiple choice part, is the 4 basic rules of probability. These 4 basic rules are for chapter 4, and then we're going to see them kind of transition into chapter 5 as well as chapter 6. Probabilities are always between and including 0 and 1. The probability of an impossible event is 0. The probability of a certain event is 1. And then the sum of all the probabilities of the outcomes in a sample space is 1. All right. So with that, we're going to turn and we're going to talk about a type of probability called classical probability. So again, I'm going to use something that's filled in, and we'll kind of go little by little. But one of the main things about this first lesson is what we say is the approaches to probability. There are 3 approaches to probability. We call those approaches classical probability, empirical probability, or subjective probability. Classical probability can also be called theoretical probability, and here relative frequency probability or experimental probability are other terms for empirical probability. Subjective probability is just subjective probability. So classical probability uses sample spaces to determine the numerical probability of an event will happen. Classical probability assumes that all outcomes in the sample space are equally likely to occur. So here are some things to fill in. I'm going to talk about them. I'm not going to read them word for word. You can pause and get them down. So it does give you a formula for calculating probability through the classical approach. I did identify what the notation means in each one, but ideally everyone in this course should already know how to make a basic probability question where we're looking at the number of outcomes that we're trying to calculate the probability for over the total number of outcomes in the sample space. So this is really a lot of the probability in these notes is basic probability. I'm keying in on how to identify that we're using a classical probability approach. There are some rounding rules for probability as well. You do want to make sure you get these down and we follow them. I'm going to move on past them, so you could pause the video at this point and write them down and then unpause when you're ready to go again. What you're going to see is that in the following examples, a deck of cards is often used as an example for probability. Typically, it's a classical probability approach, but it doesn't have to be. I did do some of the examples below, but there's no need really to do them all. Getting the actual answers to these probability questions at the bottom of the page is basic probability. The one thing you will have to be familiar with is a deck of cards. A deck of cards is made up of 52 total cards. There is 4 different suits of cards, and then within those suits, there are 13 cards, an ace, and then card numbers 2 through 10, and then a jack, queen, and king. Probability of picking a 4 in a standard deck of playing cards. So 4 is our event. There are 4 4s in the deck of cards out of 52. We can represent it in fractional form or as a decimal. If you notice, I skipped over various examples, and here's another one. Probability rolling a 4 on a die. So my probability notation looks the same, P of 4, but the 4 is 1 out of 6 outcomes, right? And I also have the bottom two, so I'm just going to kind of reveal both of them. Number 5, probability of rolling an odd number. An odd number contains multiple outcomes, so it's a compound event. There are 3 out of 6 numbers that are odd. Number 6 lends itself to doing a quick tree diagram because you're tossing 2 coins. So just being able to look at that sample space may be a little bit helpful, and identifying the probability that both of them land on tails. Well, there's only 1 out of the 4 outcomes. Classical probability, if you think about it, when you toss a coin, we consider that it's equally likely to land on heads as it is on tails. When you rule a fair side